This is Eratosthenes. He calculated the circumference of the Earth in the year 240 BC using only a stick and some basic school maths. In this video, you can either try this yourself or follow along to see how I copied his method. All that you need to try this experiment yourself is to know the distance from your town to the equator in kilometers. You can use Google for this. A stick of some kind, a ruler for measuring, and some basic trigonometry knowledge as well as a calculator. This experiment can be done on a solstice or an equinox. These are the days of the year when the sun is almost directly overhead at the equator at solar noon, which you can also find using Google for your location. We measure on these days and times so that we know that there is no shadow at the equator, and because of this we know that the size of our shadow will be directly related to our position on the globe. First, we need to know our distance from the equator in kilometers or meters. Eratosthenes didn't have Google, so he had to pay somebody to walk from Alexandria, Egypt to the equator and measure his steps, but luckily we can use Google and save some money. I measured my shadow in the United Kingdom. It is a small country, so I won't specify a city, but if you live in a large country, you should find the latitude of your city, not your country, for a more accurate result. Next, we need to go outside and measure the shadow. You should hold your stick or pen upright so that it makes a right angle with the floor, similar to a lamp post or a tree. Make sure that you do this at solar noon on a solstice or equinox. Write down the length of your shadow and the length of your stick for later. In my experiment, my stick was 14 centimeters, or 0.14 meters, and my shadow was 18 centimeters, or 0.18 meters. Draw a right angle triangle and put these measurements on the sides, remembering which side is the shadow and which side is the stick. Now that we have all of the information we need, we just need to apply some trigonometry and geometry to find the circumference of the Earth. We will start by finding the angle at the top of our stick. To find the angle at the top of our stick, which is called x on the diagram, we use the tangent rule. If you are following along, substitute your own values in as the opposite and adjacent sides. The sun is very far away. That means that when its light rays arrive at Earth, they are all approximately parallel. This is good news for us, because the rays line up with our triangle, as well as lining up with the centre of the Earth. We can use the alternate angles rule to see that the angle between our location on the Earth and the equator is approximately x, the value that we just calculated. We now know our distance from the equator in kilometers and in degrees. Now we only need to find out how many of these segments make up the entire circumference of Earth. Since a circle always has 360 degrees, we can divide 360 by the angle x that we calculated earlier. In my example, this is 360 divided by 52.1. And we see that in my example there are 6.91 segments. Simply times the number of segments by your distance from the equator to get the full circumference of the Earth. I calculated the Earth to have a circumference of around 42,500 kilometers. A quick check on Google tells me that the Earth has a circumference of around 40,000 kilometers. That means that I was only 5% over. That's a pretty accurate estimate, and hopefully you can get a good result like this, or maybe better if you try it yourself. The original calculation was conducted by the Greek polymath Eratosthenes in Alexandria, Egypt, in around 240 BC. It was commonly known that the Earth was round in those times, but it wasn't clear just how big it was. After hearing that there was a town to the south of his town, where the sun was directly overhead on a certain day of the year, he employed a man to measure the distance to this town from his own, on foot, and used this measurement, along with his measurement of a shadow in his hometown of Alexandria, to calculate the Earth to be 46,250 kilometres, which was a pretty amazing level of precision, considering how early in history this calculation was done, and using such basic rules of trigonometry. Here on this slide I've put a recap of the full method on one page so that you can pause the video or print off the slide. You can find the dates of solstices and equinoxes quite easily online, but here are a few of the upcoming ones to save you some time. If you're still watching the video at this point, thank you for watching. And if you're struggling with maths at the moment, you can find details in the description of this video to have an online tutoring session with me.